Hello everyone, thanks for tuning in. This is Mingkun Chen from Jonathan Fan's lab at Stanford University. The topic I'm going to present today is reparametrization to incorporate constraints in the inverse design of nanophotonic devices. Metasurfaces are artificial media with subwavelength scale patterns that are able to control the propagation of light by wavefront shaping. They have been demonstrated for a broad range of applications from sensors to image systems and integrated optics. Inverse design use topology optimization has proven to be highly effective to design metasurfaces with optimized performance. Here shows some inversely designed free-form metasurface devices. And we can see that with topology optimization, we're really able to push the design limits and design metasurfaces with extremely high efficiency. Topology optimization based on adjoint variable method is an iterative optimization process based on gradient descent or gradient ascent. Here on the right, we're looking at the top view of a unit cell of a deflector. We optimize the material distribution or the shape of the pattern for a certain design objective. And we start with a randomized dielectric continuum or grayscale pattern, which gradually converges to a binarized pattern. In this case, a pattern that contains only silicon and air. During each iteration, the gradient of each pixel can be calculated from a forward and an adjoint EM simulation. In most design problems, there are various constraints for the design variables. One type of the most important constraint is due to fabrication considerations. This is to say, we want to design devices that are fabricable. When we have constraints in an optimization problem, it's the same as adding boundaries to the original design space. Thus, it's only necessary to search within this subset of subspace of the original design space when we look for optima of this constraint problem. In this case, since we have a smaller design space, sometimes we can be more efficient by reducing the number of parameters to describe the design space. For example, in topology optimization, we use thousands of pixels to describe the design space of free-form devices. However, since we can never have single pixelated pattern, which is far beyond the fabrication ability and minimum feature constraints, it is a waste of resource to describe the pattern in the pixelized space. We don't need that many degree of freedom. So here I will introduce how we use a low-dimensional space to reparameterize and more efficiently describe the constrained design space. We use this freeform 2D diffraction grating as an example. Here, each period contains silicon nanoridges on top of silicon dioxide substrate. And the efficiency we're optimizing for is defined as the power in the output direction over the total instance power. In conventional topology optimization, the pattern is described by the permittivity at each pixel. And the width of each pixel can be only a few nanometers. However, it is unrealistic to have silicon nanoridges with only 1 pixel wide. Here shows some SEM images of cross-section of nanoridges. We can see that due to fabrication limits, we don't want too small of a feature size. So in the design process, we would always like to put some constraints on the minimum feature size. However, it is actually not easy to directly enforce this minimum feature constraints in the pixelized space. Existing techniques such as adding penalty terms in the figure of merit or applying threshold filters are able to push devices towards regions of design space that satisfy the desired constraints, but they don't guarantee the enforcement of constraints. Here we impose hard constraints in optimization by reparameterizing the problem. Since the constraint is directly enforced onto the width of each material, it makes more sense to use a vector that describes the width of each silicon or air bar as the design variable. And thus we have more than an order of magnitude reduction in the dimension of design space. So now the constraints can be clearly formulated as the two equations on the right, where each width need to larger or equal to the minimum width, which is W mean, and the summation of the width should be equal to L, which is the period of the structure. And with some simple math tricks, we can further reduce the design space into independent parameters and get rid of the constraint. So to summarize the idea, we initially define devices in latent space free of constraints, and then transform these devices to a physical device space with hard constraints using analytic and differentiable mathematical transformations, where we call it reparametrization. These devices are evaluated and optimized in this physical device space, and modifications to these devices are mapped back to their latent representations. Now I will briefly introduce how this reparametrization can be incorporated into the conventional topology optimization. We know the traditional topology optimization is an iterative process where gradient on the permittivity profile can be calculated to update the pattern. Adding reparametrization is simply adding one more mapping from the latent vector to the pixelized pattern. And since all the mapping functions are differentiable, we can easily get the gradient for the latent vector from backpropagation. So every iteration, we actually update the latent vector in this low-dimensional reparameterized space. I would like to point out that through this reparameterization scheme, we frame the constraint optimization problem as a boundary optimization with definitive topologies. Here summarizes some preliminary results. This graph shows with a fixed number of bars, in this case we have 6 bars, the graph shows how the deflection efficiency changes with increasing minimum feature size. And this shows a sample run for when the minimum feature size is 60 nanometers. So during each iteration, instead of change the pattern in pixel scale, the pattern changes according to variation in the width of the bars, where the width parameters strictly follow the minimum feature constraint through the whole course of optimization. Also, in order for the gradient to be able to backpropagate, we relax the pattern into grayscale at the very beginning and gradually binarize it. Until here, what we achieve is a local optimizer. In other words, the final optimized pattern is definitive once we have the initial topology. In fact, this reparametrization scheme can be further developed into a global optimizer. It is compatible to the global optimization scheme our group recently developed. It is named as Global Topology Optimization Networks, or GLONet for short. The idea of GLONet is to perform optimization over a distribution of devices during each optimization. So shown here, a generative neural network is used to produce latent vectors, the inputs of which is a uniformly distributed random noise vector z. Different z maps onto different latent representation of the device, so that the generator is able to produce an ensemble of devices that cover the design space. Instead of updating individual device patterns in each iteration, GLONet updates the generator by backpropagating all their efficiency gradients through the network. In the optimization of the generative network, the weight of each neuron is updated using the efficiency gradients of all devices. Since all different device patterns share the same generator, the generator knows the efficiencies and gradients of the whole device ensemble, so that the distribution of the generated devices evolves as a group as shown on the right. Therefore, a more promising part of design space will be explored in the next iteration, and the distribution of generated devices will gradually converge to a high-efficiency cluster. Therefore, non-global optima can be mostly avoided. Here we showcase the optimization process of the reparameterized glow nets by looking histograms of generated device efficiencies and images of representative physical devices as a function of iteration number. With a total of 100 iterations, at the very beginning, the generative network outputs a diverse distribution of grayscale devices. This indicates that the network is broadly sampling the device design space in its search for good optima. The performance histograms shows mostly modest to low efficiency devices. At later iterations, the network has identified and converged to more narrow regions of the design space and outputs less diverse distributions of devices. Over the course of optimization, the devices become more binary and the distribution of generated devices narrows and shifts to high efficiency values. The final network produces binary devices that are clustered around the global optimum. After incorporating the reparameterization scheme into GlowNet and developed a global optimizer with physical constraints enforced, here I would like to revisit this graph showing how the deflection efficiency changes with different minimum feature size. The red line marks the globally optimized devices, and we see a substantial improvement in efficiency comparing to results from the local optimizer. Here shows globally optimized devices with different minimum feature constraints. The top right device is the global optimal device when we set the minimum feature size as 20 nanometers. It is the same device we get from unconstrained global optimization, as well as other optimal with minimum feature sizes equal to or smaller than 20 nanometer. We can also see a general trend that as we increase the minimum feature size constraint, the globally optimized performance decreases. This is simply because we are searching within a smaller design space as we increase the constraints. We have also performed global optimization for different topologies. Each curve here shows the case with a different number of bars. We can see that certain topology outperforms others for certain range of minimum feature constraints. Since we can get distinctly different topologies as a function of minimum feature size, it is important to incorporate minimum feature size through the whole course of optimization, because we can't just take the best device without constraints and then adjust it to incorporate constraints afterwards. Until now, we are able to perform global search for fixed topology devices, while a proper global optimizer requires the ability to search for the proper device topology as well as the detailed layout for that topology. With what we have shown here, and optimizers for fixed topology devices, we can perform this task by parametrically sweeping across a wide range of topologies, like what we just saw. But this can be computationally intractable when scaling to complex systems. So in the last part of this presentation, we show that reparameterized glow nets can combine concepts in boundary and topology optimization to globally optimize geometrically constrained devices with variables topology. Here outlines the concept. As before, with fixed topology optimization, we subdivide the device permittivity profile into M sections. However, instead of assuming that a given section is either silicon or air, we define each section to have two parameters. Wi denotes the section width, and epsilon I denotes the permittivity at the center of each section. A range of topologies can now arise because adjacent sections in final binarized devices can have either the same or different permittivity value. The permittivity profile of the entire structure is calculated by smoothly connecting the permittivity at the center of each section using a piecewise transformation. So then in the newly configured glow nets, two separate generators are used to produce distributions of width and permittivity vectors, which are combined to produce constrained physical devices. Again, we look into the optimization process by looking at the histograms of efficiencies and images of representative devices as a function of iteration number. Near the beginning of the optimization, at iteration number 5, GlowNets generates a wide range of random devices with different topologies. As the training process evolves, the device distribution gradually converges to a narrow range of topologies, and by iteration number 50, we have collapsed onto a single device topology. So then GlowNet subsequently focuses only on boundary optimization to refine the for-rich device layout. At the end of training, the generated devices are clustered around the global optima. So finally, here we revisit this graph and show benchmark analysis of our variable topology reparameterized glow nets. By comparing with the fixed topology case, which is shown in the dashed line, we see that our variable topology scheme is able to search for the correct device topology for a given minimum feature size constraint. Furthermore, the best variable topology devices, which is shown in the solid line, largely follow the performance of the best fixed topology devices. This indicates that this new variant of GlowNets can effectively perform a reparameterized boundary optimization. To summarize, in this work, we are able to incorporate hard physical constraints into the inverse design process, and we showcase by designing high-efficiency beam deflectors with guaranteed minimum feature size. And we can do global optimization by combining these techniques with generative neural networks. With that said, I would like to conclude my presentation, and thank you so much for listening.